Ali. Oh, let's see. Okay, I have to say we're being recorded. Yes, I agree. Hello, I'm Gizem Karali. I'm professor of mathematics at Pomona College, California, USA. Welcome to today's event. This is the 6th talk of the monthly distinguished colloquium series in pure and applied mathematics organized by the Turkish Mathematical Society. So information about upcoming talks and recordings of previous talks is available online. I'll put the link to the chat for those of you who may want to click around and look to see. And we hope that you will use the chat today to think about and ask questions about and advance this conversation that we will have today throughout this next hour. So I wanted to introduce you to today's speaker, who's Professor Stephanie van Willigenburg. Steph obtained her PhD in 1998 from the University of St. Andrews, Scotland. Then she did postdoctoral fellowships at York and Cornell before joining the University of British Columbia, where she held an NSERC University Faculty Award for 5 years. And then she has risen through the ranks, and since 2012, she's a professor of mathematics there. So Steph is an outstanding scholar and expert in algebraic combinatorics. She's made significant contributions to the combinatorial understanding of a variety of special functions. Her earlier awards for research include the Peter Wall IAS Early Career Scholar Award in 2004 and a Humboldt Research Fellowship in 2008. More recently, she won the Krieger Nelson Award from the Canadian Mathematical Society for Outstanding Research in 2017, and she was a Simons Foundation CRM professor in 2018. Steph is also an excellent teacher and an inspired communicator of mathematics. In 2007, she won a Killam Award for her teaching. She has given numerous plenary lectures, including at Formal Power Series and Algebraic Combinatorics in 2015, gave an invited address at the AMS meeting in 2016. And in January 2019, when we were still meeting in person for doing mathematics together, she gave an invited address at the joint math meeting. Steph is currently the Associate Head for Research in the UBC Math Department and is one of the co-founders of the Algebraic Combinatorics Research Community to foster mentoring, collaboration, and networking for women in algebraic combinatorics and related areas. So I'm delighted to be here today to listen to and learn from Steph, Professor van Willigenburg, about the 3+1 free conjecture of chromatic symmetric functions. Welcome, and take it over from here, Steph, please. Thank you.
Thank you, Gizem, for that wonderful introduction. Thank you all for coming this evening, and also thank you very much to the organizers for inviting me. I'm really honored to be speaking today to the Turkish Mathematical Society. And so what I'm going to be doing today, as Gizem mentioned, is I'm going to be telling you about the 3+1 free conjecture of chromatic symmetric functions. And if you don't understand any of those words, don't worry, we'll be introducing them all as we go along. And as Gizem said, if you have any questions, please put them in the chat, because all of your faces and the chat are over there on a second screen, so I can't see them. And then she'll read them out and I'll be able to answer them. So before we get going, I'll just do a quick tech test. So, okay, and this is why we do this. Has the slide moved on? Yes? Okay. And in that case, then what I will do, I will start. So thank you very much. Now, before we actually get on to the chromatic symmetric function, we're going to go back in time a little bit to the chromatic polynomial, and give me a thumbs up if you can hear me clearly. Yep. Okay, wonderful. Thank you. So we're going back to 1912 and to Birkhoff, who was trying to solve what became later known as the four-color theorem. And his method for doing this was to try and use the chromatic polynomial, and that in turn has ended up becoming an area of research on its own. So what is the chromatic polynomial? Well, if you're given a graph G, so that's a set of vertices connected by edges, then we say a proper coloring of the vertices is going to be, well, you're going to color those vertices so that if two vertices are joined by an edge, then they have to be different colors. And so in particular, this example right here is not a proper coloring because we have two vertices joined by an edge and they happen to be the same color. However, this is a proper coloring because you have two vertices joined by an edge and they are different colors. So with this in mind, the chromatic polynomial then is going to be the number of proper colorings of your graph with k colors. So let's do a quick example. So since it's late in the evening for you and early in the morning for me, we're going to keep it pretty nice and small. So let's try coloring this graph right here. Well, if I try and color this first vertex, I have a choice of k colors. Then when I go to the second vertex, I've used one of them up, so I've got k-1 colors. And then with this one right here, again, I've used up another color, so I've only got k-2 colors to choose from. So therefore, the chromatic polynomial, the number of ways of coloring, is going to be k times k-1 times k-2. Now, this heuristic, while being very nice, doesn't always work, but what does always work is deletion contraction. So I'm going to tell you about that next. So for that, we need to know how to delete and contract on a graph. So to delete an edge E, all you do is you remove your edge E to get G delete E. And if you contract E, then what you're going to do is you're going to take your edge, you're going to shrink it, identify the vertices to get G contract E. So here, if we shrink, we get this graph right here. And then with this in mind, then deletion contraction says that the chromatic polynomial of G minus... Could someone please mute David? Thank you. So that doesn't happen in real life either. The chromatic polynomial of G minus that of G delete E plus that of G contract E is equal to 0. So with that in mind, let's get on to our main function of study, the chromatic symmetric function. And this is a lot more modern. This dates from Richard Stanley at MIT from 1995. So again, what we're going to be doing is we're going to be coloring our vertices such that if two vertices are joined by an edge, they've got to be different colors. But now what we're going to do is instead of restricting ourselves to K colors, we're actually going to have a much larger paint box and we're going to have infinitely many colors. But then the main difference is going to be we're now going to start associating a monomial to each of our colorings, and that extra piece of information is going to make a massive difference. So how do we do that? Well, given a proper coloring of our vertices, we're going to associate a monomial to it. And so this monomial is going to be in commuting variables x1, x2, x3, and so on. And what we're going to do is we're just going to give x the color on vertex 1, x the color on vertex 2, x the color on vertex 3, and so on. So for example, if cyan is color 1, magenta is color 2, and lime is color 3, then this coloring right here is going to give us x1, x2. Then this coloring right here is going to give us x2, x1, but since our variables commute, that's going to be the same as x1, x2. And then this coloring right here is going to give me x1, x3. Then with this in mind, we're able to define the chromatic symmetric function. So what we're going to do is we're going to have a proper coloring. Then what we're going to do is we're going to make all of the monomials corresponding to it, and then we're going to add those all up. So let's do an example. Okay, so let's take this graph right here. And again, cyan's going to be color 1, magenta color 2, and lime is going to be color 3. then this coloring right here is going to give me x1 squared. This coloring right here is going to give me x2 squared, and this coloring right here is going to give me x3 squared. Then, as we saw on the previous slide, this coloring right here is going to give me x1, x2, and this coloring right here is also going to give me x1, x2, thusly giving me a total of 2 x1, x2. Similarly, these two colorings are going to give me 2 x2, x3, and these two colorings right here are going to give me 2 x1, x3. Now, sadly, deletion contraction no longer works because when you contract, you're going to end up losing a vertex, you're going to end up losing a variable, so you're going to have a degree change. But instead what we have is the beautiful triple deletion rule of Oriana and Scott from 2014. So what they were able to prove is the following. So let G be a graph such that the edges E1, E2, and E3 form a triangle. Then the chromatic symmetric function of G minus that of G delete E1 minus that of G delete E2 plus that of G delete E1 and E2 is going to be equal to 0. And in actual fact, it turns out that you can actually generalize this from a triangle to a K-cycle. And so this was done by myself and Samantha Delberg in 2018. So in this case, what you do is you have your edges E1, E2, E3, all the way up to EK. And then you're going to fix EK, and you're not going to do anything with it anymore. So once you have that, then what you're going to do is you're going to take the chromatic symmetric function of G, delete a subset of those edges, and those are going to be any one of E1 up to EK minus 1. You're going to have an appropriate sign, and then you're going to add those all up, and you're going to get 0. So that's K deletion. Now, one thing to note is if you then additionally put weights on your vertices, you can actually get deletion contraction back. And that's due to Crew and Sperkel at the University of Waterloo in 2020. Now, I've kept saying that the chromatic symmetric function is a symmetric function. So let's justify that. So a symmetric function is simply a formal power series in commuting variables, such that for all permutations, if you have your function and then you permute the variables, you get your function back. And so notice that our chromatic symmetric function is indeed a symmetric function, because what you can do is, well, if you've got any proper coloring, then if you permute the colors, you'll get another proper coloring. And so therefore you've got a symmetric function. And so this chromatic symmetric function is going to lie in the algebra of symmetric functions. So let's have a look at a few of the bases of our algebra of symmetric functions that are going to show up later in the talk. So the first classical basis we're going to look at is that of Powersum symmetric functions. Now, before we get started, we're going to need an indexing set for our algebra, and that's going to be the set of all partitions. So a partition lambda consisting of lambda1 greater than or equal to lambda2 greater than or equal to lambda3 and so on of n is just going to be a list of positive integers whose sum is n. So for example, 3, 2, 2, 1 is a perfectly nice partition of 8 because 3 plus 2 plus 2 plus 1 is 8, and these numbers are weakly decreasing as you read them from left to right. So with this in mind, let's define the ith Powersum symmetric function. That's going to be pi, and that's simply going to be x1 to the I plus x2 to the I plus x3 to the I, and so on. And then given a partition, lambda, p lambda is going to be p lambda 1 times p lambda 2, and so on. So let's do an example. So we wanted to compute p21. Then by this definition right here, this is equal to p2 times p1. And then by this definition right here, p2 is going to be x1 squared plus x2 squared plus x3 squared, and so on. And P1 is going to be x1 plus x2 plus x3, and so on. And so what Stanley was able to prove in 1995 was a beautiful formula for the chromatic symmetric function in terms of Powersum symmetric functions. So let's look at that next. And for this, we're going to need a little bit more. So given a subset of edges, lambda of S is going to be the partition determined by the connected components of our graph G restricted to our subset of edges S. So let's look at an example. So say this is our example right here. Then the graph G restricted to the edge E2 is this graph right here. And if we look at the size of the connected components, we get 2, 1, giving us the partition 2, 1. So with this in mind, we have the following theorem from Stanley. The chromatic symmetric function of some graph G is going to be, well, you're going to take all possible subsets of edges. Then what you're going to do is you're going to look at the partition determined by the connected components, make the Powersum corresponding to that, along with an appropriate sign, and then you're going to add those all up. So with that in mind, let's do an example. Okay, let's go back to our running example right here. So our graph G restricted to, well, both the edges E1 and E2 is this graph right here. And looking at the sizes of the connected components, we're going to get 3, giving us a P3. Then if we look at the graph restricted to E1, we get this graph right here. And looking at the size of the connected components is going to be 2, 1, giving us a P21. If we look at our graph restricted to the edge E2, we're going to get this graph right here. And looking at the size of the connected components, we're going to get 2, 1, giving us another P21 along with the appropriate sign. And then if we're going to restrict ourselves to no edges whatsoever, we get this graph right here. And if we look at the size of the connected components, we get 1, 1, 1, giving us a P 1, 1, 1. Now we're going to be looking at a second basis, which will show up later, that of elementary symmetric functions. So the ith elementary symmetric function EI is simply going to be a sum of monomials with I variables such that these indices right here are increasing. And for lambda being a partition, lambda 1, lambda 2, and so on, E lambda is then simply going to be E lambda 1 times E lambda 2, and so on. So let's do an example. So say I wanted to compute E21. Well, by this definition right here, this is going to be E2 times E1. And then by this definition right here, E2 is going to be a sum of all monomials consisting of 2 variables whose indices are increasing. So this is going to consist of terms like x1, x2, x1, x3, x2, x3, and so on. And then E1 is just going to be a sum of single variables, so x1 plus x2 plus x3, and so on. Now, Stanley was also able to prove an expression for the chromatic symmetric function in terms of elementary symmetric functions, but it's not as nice as the one for the Powersum symmetric functions. Nonetheless, it's really very cool, so we'll look at that right now. So he was able to show that if you write your chromatic symmetric function as a sum of elementary symmetric functions with coefficients, then, well, if you add up these C lambda, where you add up all of the lambdas that have K parts, then you get the number of acyclic orientations with K sinks. So what's one of those? Well, if you take your graph and then you start putting directions on all the edges, then you say you have an acyclic orientation if you cannot go round in a cycle when you follow the arrows. So that's an acyclic orientation. And we say that a vertex is a sink if you look at your vertex and all of the arrows are coming inwards. So with this in mind, let's look at an example. So if we take this graph right here and say we want to look at the coefficient of E3.
Steph,
Okay.
there's a quick question.
Yes.
So does that mean all coefficients are non-negative?
Oh, that is a brilliant question. And hi, Eski, wonderful to see you again. That is fantastic, because you have already seen one of the major questions that's going to be coming up later in the talk that have kept people busy for 25 years, because it turns out that sometimes these numbers here, they're positive, they're negative, but miraculously they cancel to give you the number of acyclic orientations with K sinks. So amazing question. The answer is not always, and it's super difficult to tell when, and that's coming up later. Thank you so much. So thank you. Brilliant. So with that in mind, hold on to your hats because that's coming up later. But for the time being, let's return to our example. So remember, what we're doing is we are looking at the coefficient of E3 that has one part. And so what we need to do is look for the number of cyclic orientations with one sink, of which there's 1, 2, 3. So our coefficient is 3. And if we want to look at the coefficient of E21 with 2 parts, then we look for the number of acyclic orientations with 2 sinks, of which there is 1. So our coefficient is 1. And for our third basis of interest in this talk, we're going to need to introduce a little bit more notation. We're going to need to introduce what's known as diagrams. So recall, we've got our partitions, a list of positive integers that are weakly decreasing. And so given your partition, the diagram of the partition is made as follows. So what you're going to do is you're going to take your partition, and the diagram is simply going to be the array of boxes with lambda I boxes in row I from the top. So if we take our running example 3, 2, 2, 1, then this is going to have 3 boxes in the top row, then 2 in the second, then 2 in the third, and 1 at the bottom. And just to keep things neat and tidy, we're going to left justify them. And then what we're going to do is we're going to fill that diagram with numbers to make a semi-standard Young tableau. So we say that a semi-standard Young tableau of shape lambda is going to be a filling of the boxes of our diagram with the numbers 1, 2, 3, and so on. So the rows weakly increase as we go from left to right, and the columns strictly increase as we go from top to bottom. So notice this is a perfectly nice semi-standard Young tableau. Look at those rows weakly increasing, 1, 1, 1, 2, 4, 4, 5, 6, and look at our columns strictly increasing, 1, 2, 4, 6, 1, 4, 5, 1. And then given a semi-standard Young tableau, again, we can associate a monomial to it. We're just going to do x1 to the number of 1s we can see, x2 to the number of 2s you can see, x3 to the number of 3s you can see, and so on. So again, going back to our example right here, the monomial associated to it is going to be x1 cubed, x2, x4 squared, x5, x6. And then with this in mind, we can define our last basis for this morning, which is going to be that of Schur functions. So given a partition lambda, the Schur function S lambda is going to be, well, first of all, we need to make all semi-standard Young tableau of shape lambda. Then we're going to make the monomial corresponding to it, and then we're going to add them all up. So for example, say we wanted to make the Schur function S21. The first thing we would do is make all of the semi-standard Young tableau of shape 2, 1. And well, if I made all of them, we'd be here for quite a while. So let's just restrict ourselves at the moment to all the ones just containing the numbers 1, 2, and 3. Here they are right here. Then if I look at this one right here, this is going to give me the monomial x1 squared x2. This one here is going to give me x1 x2 squared. And then if I move over to the right-hand side, this one's going to give me x1, x2, x3. This one's also going to give me x1, x2, x3, thusly giving me 2x1, x2, x3. And the formula for our chromatic symmetric function in terms of Schur functions is not quite as nice. It's really based off symmetric function transition matrices, and you need to combine a couple of them. So then you're combining two different combinatorial models. And this was put together by Wang and Wang in 2020. And so now we're going to start moving on to E-positivity and Schur positivity, which are going to be central to the 3+1 free conjecture. So we say that a graph is E-positive if its chromatic symmetric function is a positive linear combination of elementary symmetric functions, and is Schur positive if its chromatic symmetric function is a positive linear combination of Schur functions. So if we look at our running example, note that it is both E-positive and it's Schur positive because we see a lot of nice positive coefficients. However, this thing right here, which is known as the claw or K13, which is also going to play a starring role later, is not E-positive and it's also not Schur positive. In fact, it's actually the smallest graph that is not E-positive, and it's also the smallest graph that is not Schur positive. And so because of this, it was really felt that, well, this claw is really kind of the crux of the matter to E-positivity and Schur positivity. It's kind of the minimal building block. Now, E-positivity and Schur positivity are very closely related, because if you want to write your elementary symmetric functions in terms of your Schur functions, well, there's a really beautiful formula for it. And in particular, there's a beautiful formula for calculating the coefficients. So if you want to compute this coefficient K mu lambda, well, this is simply going to be the number of semistandard Young tableau of shape mu filled with lambda 1 1s, lambda 2 2s, and so on. And then what is this thing here? Well, this is mu transpose. It's the transpose of mu along the downward diagonal. Now, what do I mean by that? Well, what I mean is that what you're going to do is you're going to take your diagram, you're going to grab it along the main diagonal, and you're going to flip it. And once you do that, you're going to make the transpose. So just grab your diagram and flip it to make mu transpose. So let's do an example. So say I wanted to compute E21. Then what I'd want to do is I'd want to make all of the semi-standard Young tableau that have 2 1s and 1 2. So here they are right here. Then what I would do is grab my diagram and flip it along the diagonal. With this one, it's going to give me 2 1, giving me an S21. And then with this one, when I flip it down here, I go from a row to a column, giving me 1 1 1 and the Schur function S1 1 1. So why do we care about E-positivity and Schur positivity? Well, if a symmetric function is E-positive, then it's related to permutation representations. And as we just saw on the previous slide, we have a way of computing the coefficients when you turn an elementary symmetric function into a sum of Schur functions. So therefore you have that E-positivity implies Schur positivity. And if something is Schur positive, then it arises as the Frobenius image of some representation of a symmetric group. And also it arises as the character of polynomial representation of a general linear group. And what's going to be important to us today is that we have the Stanley Stembridge conjecture. So let me tell you about that next. So the Stanley Stembridge conjecture says that if G is an incomparability graph of a 3+1 free poset, then its chromatic symmetric function is E-positive. So let's unpack that statement. Well, we know what it means for a chromatic symmetric function to be E-positive it's going to be a positive sum of elementary symmetric functions. So let's look at what it means to be a 3+1 free poset or partially ordered set. Well, we say a poset or partially ordered set contains 3+1 if you have 3 elements all in a chain and then one that's incomparable. And so something is 3+1 free if it does not contain this. Now let's move on to what it means to be an incomparability graph. Well, we say that if you have a graph, if you have your poset, then, well, to make the incomparability graph, what you do is if 2 elements of your poset are incomparable, then you're going to make them adjacent in your graph. Now, that conjecture still stands, but what Gasharov, who's at Cornell, was able to prove in 1996 was the weaker statement, that if G is an incomparability graph of a 3+1 free poset, then its chromatic symmetric function is sure positive. And in actual fact, we don't have to work with the conjecture in that statement because Guy Paquet was able to show that it was enough to prove it for what's known as unit interval graphs, namely a connected intersection of complete graphs that are lined up in a row. So recall that the complete graph is going to be, well, if you want the complete graph on n vertices, you take your n vertices and you make every single pair of vertices adjacent. That gives you your complete graph. And then if you want to make a unit interval graph, you line up a bunch of them in a row and smush them together. Now, there's a technical definition, but since it's early in the morning for me and late in the evening for you, it's good enough to know that we've got a bunch of complete graphs that you smush together. So for example, right here, we've got a K3 that's been smushed together with a K5 along a vertex that's been smushed together with a K4 along an edge. And so with this in mind, we can reformulate the Stanley Stembridge conjecture as follows. If G is a connected intersection of complete graphs, then G is E positive. Now, while in general, the conjecture is still open, there are known cases for which the conjecture is true. So back in 1993, Stanley and Stembridge proved that the conjecture was true for 2 complete graphs intersecting. And then in 1995, in his original paper on the chromatic symmetric function, Stanley showed that the conjecture was true for 2 complete graphs, K2, intersecting at vertices. So here's a K2, here's a K2, here's a K2, here's a K2. And when you put them all together, you get a graph that's known as a path. And then in 2001, Gebert and Sagan were able to show that the conjecture was true for complete graphs intersecting only at vertices. So here we have a K4 intersecting only at a vertex with a K5, intersecting only at a vertex with a K3. And then Samantha Dalberg in 2018 was able to show that the conjecture was true for complete graphs K3 intersecting only at edges. And now what I'm going to do is I'm going to talk about some results hot off the presses that I was able to show with my research group consisting of my postdoc Fareed Ali and Ifad and my undergrad research student Victor Wang. So what we're going to first of all do is we're going to redraw our complete graphs. So what we're going to do is we're going to put all of our vertices in a row and then connect every pair of vertices up. And remember, that is the definition of a complete graph. So we've got our complete graph right here. And then with this in mind, we're able to prove the following new cases for the Stanley Stembridge conjecture. So we have E positivity for ice cream scoops. So what we're going to do is we're going to take the complete graph and we're going to melt edges away from the right or the left. In this case, we're going to do it from the right. So I'm going to locate some edges on the right and melt them away. Melt, melt. And that's going to give me an ice cream scoop. And notice that this is an intersection of two complete graphs. Notice you've got a complete graph underneath the cyan edge, and then you've also got a complete graph taking all the vertices underneath the magenta edge. We also have e-positivity for snowy peaks. So in this case, what we're going to do is we're going to take the complete graph and melt one edge away and then add a dribble from the right or the left. In this case, we're going to do it from the left. So the first thing I'm going to do is melt that top edge away right here. And then I'm going to add some dribbles. So I'm adding them on the left. Here's a dribble, here's a dribble. And notice that this is also an intersection of complete graphs, because I can take all of the vertices underneath the cyan edge, all of the vertices underneath the purple edge, and all of the vertices under the magenta edge, and each of those themselves are going to be complete graphs. We also have e-positivity for peaky snows. So now what we're going to do is we're going to take the complete graph and we're going to melt edges away, and then we're going to add one dribble. And we can do this again either from the right or the left, but in our case, we're going to do it from the right. So here's our graph, and we're going to melt away our edges, and then we're going to add just one dribble right here. And notice that this is an intersection of complete graphs as well. We have all of the vertices underneath the magenta edge, all of the vertices underneath the purple edge, and all of the vertices underneath the cyan edge. And in fact, from these building blocks, we can actually do many more cases of the Stanley Stembridge conjecture, because we were able to show that if G is a connected intersection at the rightmost and leftmost vertex of any combination of ice cream scoops, snowy peaks, peaky snows, complete graphs, or triangular ladders, the result is E-positive. So notice that this massive graph right here, we know straight away is going to be E-positive, because here you have yourself a peaky snow, and then you're going to join it with the rightmost and leftmost vertex to an ice cream scoop, and then join again the rightmost and leftmost vertex of a snowy peak. Now, as we know, one of the ways that we can often attack a conjecture is to actually widen the conjecture, prove the wider conjecture, and then we'll get the original conjecture for free. So what we're going to do right now is we're going to widen the conjecture to look at trees. So this is done by Samantha Dalberg, who you heard a fair bit about earlier in the talk, Adrian Shee, who was my undergraduate research student who's now at the University of Toronto, and myself. And this was published in 2020. And this is a photo of us. There's Samantha, there's Adrian at our annual research picnic. But as you can probably guess, this photograph was not taken in 2020. It was taken back in 2018. So let's look at the E-positivity of trees. Well, first of all, what's a tree? Well, a tree is a connected graph that has no cycles. So this thing right here is a tree, but this thing right here is not a tree because you've got a cycle right here. Okay, so let's have a look at trees. So if this is going to be our number of vertices right here, then here are the number of trees on that number of vertices. Notice the number goes up pretty fast. Now let's have a look at all of those trees that are E-positive. Notice that there are actually very few of them. Now notice this number is always going to be at least 1, because what you have is you always have the path. That was what Stanley proved. And then occasionally you get something else. So then it maybe makes sense to actually instead look at the opposite question. Can we prove when trees are not E-positive? And we certainly have success there. So we have that any tree with a vertex of degree at least the number of vertices taken to the log base 2 plus 1 is not E-positive. So we know that this graph right here is not E-positive, because if we look at the number of vertices, we get 6. Take it to the log base 2, we get 2 and a bit, plus 1 is 3 and a bit. and we have a vertex of degree 4. In fact, we actually believe that something much stronger is true. We actually believe that any tree with a vertex of degree 4, at least 4, is not E positive. So for example, this family right here would not be E positive. And Kai Zheng, who's at MIT, was able to prove that the conjecture is true for any vertex of degree at least 6 is not E positive. So how did we prove it? Well, there's an incredibly cool test dating from the thesis of Wolfgang III, who was one of Stanley's students. And so what we're going to do right now is we're going to look at that test. And it really deserves to be more widely known because the test itself is very simple to state, but really powerful. So for this, we need a little bit more mathematics. So we say that a graph has a connected partition of type lambda if we can find disjoint subsets of the vertices such that when you take the union of all of them, you get all of the vertices, and restricting the edges to each subset gives the connected components of a graph, each one of which has lambda-i vertices, where lambda is our partition. So let's see this in action in an example. So this thing right here, our friend the claw, has a connected partition of type 4, because if we put 4 vertices into one subset and look at the size of the connected components, we get 4. Similarly, it has a connected partition of type 3-1, because if we put these 3 vertices into one subset and this one into another, then we get connected components of size 3-1. It also has a connected partition of type 2-1-1. We put these 2 vertices into one subset, this one into another, this one into another, and we also get a connected partition of type 1-1-1-1. Just put each vertex into its own subset. But notice that it's missing a connected partition of type 2-2 because we cannot partition the vertices into a set of size 2 and a set of size 2 such that they are connected. And so with this in mind, Wolfgang III was able to prove the following. So if a graph is E positive, then it has a connected partition of every type. So in order to make our test, let's take the contrapositive. So if G does not have a connected partition of some type, then G is not E positive. So we're guaranteed from the last slide that since this does not have a connected partition of type 2-2, it is not E positive. And we can also talk a little bit about sure positivity. So what we were able to show is that any tree with a vertex of degree greater than the ceiling of the number of vertices over 2 is not sure positive. So for example, this graph right here is not sure positive because, well, we have 6 vertices divided by 2 is 3, and we have a vertex of degree 4. But these are not the only things you can say about trees. There are still many open problems. So for most of these, we're going to need the concept of a spider, because it turns out spiders are really like the building blocks of the tree problems. So a spider is simply going to be, well, you're just going to take a bunch of paths, and then you're going to join the edges to a central vertex. So say I wanted to make the spider 6, 2, 1. I'm going to have a path with 6 vertices, a path with 2 vertices, and a path with 1 vertex, and then I'm going to take their ends and join them to a central vertex. So now let's look at our conjectures. Well, remember that while Kai Zheng proved many cases, we still have the conjecture standing that we believe that any tree with a vertex of degree 4 or 5 is not E positive. But we believe we can identify some E positive tree families. So the family of spiders 2 times 2m plus 1, 2m1 is E positive. And we also believe that more generally, the family of spiders n times n factorial m plus 1, n factorial m 1 is E positive. And Kai Zheng also conjectured that if a spider is E positive, then its line graph is as well. Well, what's the line graph? Well, if you have a graph, every edge becomes a vertex, and then if two original edges touch, that becomes an edge. So because so many trees are not E-positive, that particular widening turned out not to be so useful towards the Stanley Stembridge conjecture. So let's look at a different widening. And this widening actually dates back to Stanley. And so this was recently resolved by Samantha Dalberg, who you saw earlier, Angel Foley, and myself, and it was recently published. So what was Stanley's widening? Well, Stanley in his original paper made the following statement. He said, we don't know of a graph which is not contractible to K13, even regarding multiple edges of a contraction as a single edge, which is not E-positive. But as I just said, that was the case in 1995, but 25 years later, we do. So let me tell you about that. So let's first of all unpack Stanley's statement. So first of all, it involves the claw, otherwise known as K13. And the statement involved contracting to the claw. So what does that mean? Well, it means that if you shrink edges and identify the vertices and then remove multiple edges, you get the claw. So if we look at our example down here, if you have this edge and then you shrink it, and identify the vertices, you get the claw. So this contracts to the claw. And so now let's have a look at Stanley's statement. So he said, we don't know of a graph which is not contractible to the claw, which is not E-positive. So what Stanley's statement is saying is we don't know of anything that lies outside of this Venn diagram. Okay, well, if we're going to resolve this, then we're going to need to find a good way to find out that something does not contract to the claw, which is otherwise known as claw contractible free. And for this, we're going to need to go back to 1987 and a result of Brouwer and Veldman. And they proved that a graph is claw contractible free if and only if deleting all sets of three non-adjacent or independent vertices gives disconnection. So let's have a look at this example right here. So notice that in all cases, if we delete the three non-adjacent magenta vertices, then we get a disconnected graph in each of these cases. And in this case and this case, if we delete the set of three non-adjacent black vertices, we also get disconnection. So all of these graphs are claw contractible free. Let's have a look at their chromatic symmetric functions. Well, notice that none of them are E-positive, so they all lie outside Stanley's Venn diagram. And in fact, they are the smallest counterexamples to Stanley's statement. Now, what you may say is, but Steph, hold on. Sometimes things happen at small numbers and everything gets better when you have a large number of vertices. But then I would come back to you and I would say, let me introduce you to the infinite family of saltier graphs. So what these are going to look like is the following. We're going to have this configuration in the middle, and then a path with n vertices on the left and a path with n vertices on the right. So here would be the saltier graph 3, 3. Then in this case, we were able to show that the saltier graphs are claw contractible free, because notice that if you delete any set of three non-adjacent vertices, you get disconnection. And if you look at the coefficient of E and N in its chromatic symmetric function, you get -n, n-1, n-2. So now we have an infinite family of graphs that lie outside of Stanley's Venn diagram. But then you might come back to me and say, oh, but Steph, your beautiful saltier graphs, they always have an even number of vertices. Maybe things are okay for an odd number of vertices. But in that case, I would come back to you and I would say, aha, but let me introduce you to the augmented saltier graphs. So the augmented saltier graphs is made as follows. So what we're going to do is we're going to have this configuration right here, the same as the saltier graph, and then we're going to augment it with one extra edge. And then we're going to have a path with n vertices on the left, and then a path with n or n plus 1 vertices on the right. Then, in the same way as we had for the saltier graphs, we've got our augmented saltier graphs are claw contractible free. And if you look at the coefficient of ENN or EN plus 1n as appropriate in the chromatic symmetric function, you find the negative coefficient of -n, n minus 1, n minus 2. So again, this family of graphs lies outside of Stanley's Venn diagram. But then at this point, you might say, but Steph, I was listening earlier in the talk and you said the claw was the building block to things being E positive, or with the claw not being E positive. So what happens if my graph happens to actually contain the claw as a subgraph? Okay, so then we need to look at the concept of claw-free. So claw-free simply means that we do not contain the claw as a subgraph of our graph. So looking at our two examples right here, we have our saltier graphs. They are not claw-free because here's a claw right here. But this thing right here, well, it is claw-free because if I try to make a claw, well, I'll need a vertex of degree 3. Let's pick this one. And then if I look at the 3 things adjacent to it, I don't get myself a claw because I've got this triangle. But that's not very rigorous. So instead, we're going to go back to 1970 and a result of Beinecker, how to identify a claw-free graph. So he was able to show that a graph is claw-free if there exists a partition of the edges where each partition gives a complete graph and every vertex is in at most 2 of those partitions. So let's have a look at this example right here. Well, if we partition our edges into the top triangle and the bottom triangle, and then everything else will be an edge on its own, then notice that we've got a bunch of complete graphs, a K3, a K3, everything else will be a K2, and every vertex is in at most 2 of those partitions. So this indeed is claw-free. And now let's turn this into a more general infinite family. So the triangular tower graphs are going to be made as following. So you're going to have your top triangle, your bottom triangle, a path with n vertices on the left, the middle, and the right. So here is the triangular tower 3, 3, 3. And if you want to see what it looks like in real life, this is what one of them looks like. And so you've got your top triangle, you've got your bottom triangle, and then you have your 3 vertices in a path going around the left, the middle, and the right. And so if we have a look at these graphs, well, we know for starters, they're going to be claw contractible free because if you delete any set of 3 non-adjacent vertices, you get disconnection. As we just discussed on the previous slide, they're also claw-free. And if you look at the coefficient of ENNN in its chromatic symmetric function, you get -n, n minus 1 squared, n minus 2. So again, you've got an infinite family lying outside of Stanley's Venn diagram. But again, this is not the end of the story. We believe that there are other families that lie outside of Stanley's Venn diagram. One such family is what's known as a bloated K33. So K33 was the hexagon with the crossbars, and it's going to be bloated if you pick one of those edges and you start throwing on multiples of 3 vertices, and it's always got to be multiples of 3. And then in that case, we believe we know where a negative coefficient is. We believe it's at E3 to the n, and we believe we also know what the coefficient is. We also believe that no graph exists that's connected, claw contractible free, Clawfree and knotty positive with 10 or 11 vertices. So we believe the first time we find it is our triangular tower 333 with 9 vertices, and the next case will be the triangular tower 444 with 12 vertices. And so, well, why didn't Stanley find this back in the day? Well, it's because these graphs are incredibly scarce. So if we look at the number of graphs on 6 vertices, then 4 out of the 112 connected graphs are claw contractible, free and knotty positive. And this goes to 7 out of 853 for 7 vertices, and 27 out of over 11,000 graphs on 8 vertices. And even when you find one of these graphs, those negative terms are incredibly rare. So the 293 terms in the triangular tower 777, the only negative is exactly where we said it would be in the theorem. If you look at the 564 terms in the triangular tower 888, the only negatives are where we said they would be in the theorem and at one other place. And if you look at the over 1,000 terms of the triangular tower 999, the only negatives are where we said they would be at the theorem and at one other place. So to summarize, Stanley believed that nothing lay outside of this Venn diagram. But what we've been able to show is that there are in fact infinite families that lie outside this Venn diagram, both with the claw as a subgraph and without. And so on that note, all that remains to say is that in general, therefore, the take-home message is that E-positivity has nothing to do with the claw. So on that note, let me say, Teşekkür ederim. Thank you very much for listening.
Thank you so much, Steph. This was great. This was great. Yeah, so I think we probably have some time for some questions. So I'll just open it up to the audience to see if they would like to ask questions.
I have a question, if there is no other questions.
Yes, thank you.
I'm not sure I understood it part. You said some point 3+1 free conjecture reduces to the case which is connected to complete graphs. Is there a theorem, or is this believed as a sub-conjecture? Is there a theorem that says it reduces? Or?
That's a really great question. So the reduction was proved by Matthew Guy-Paquet, and it's on the archive and everyone believes it. And some people, Farid was one of them, John Shureshin is another, have checked it, but Guy-Paquet has never published this paper. So, so that's a really interesting question. So yes, the reduction's been proved, but it hasn't been published and we don't know why. Guy-Paquet will not tell us. Thank you,
Thanks.
Great question.
Thank you, thanks.
From Dunky, thank you. Want to know how to compute the chromatic symmetric function for such large size? Yeah, that's fantastic. We actually did it on Sage Math, and we set it off on my desktop and let it run. And yeah, the triangular tower took a few weeks, and you can imagine I came in one day to UBC. This was back in the days when we could go into our offices, and the triangular tower graph was like flashed up on my screen. And I was like, ah! So I ran next door because Samantha's office was next door to mine. She wasn't in. I left a note on her laptop saying, come see me immediately. Now, apparently you shouldn't leave a note on your postdoc's laptop saying, come see me immediately, because they'll think it's something bad. But she came around, I was like, look, and we were so excited. So it was Sage Math. And so, yeah, that's been amazing at being able to compute things. And with some other larger things like Sheresian and Rammelson, what they've actually done is theoretically worked out a reduction. So say reduce graphs on 20 vertices down to 10 by just taking the essence of what was needed to be done and then run it again on Sage Math. So Sage Math is the way to go. And it's got stuff like chromatic symmetric functions and everything already built in. So it's fantastic. Thank you. Brilliant question.
Yeah.
I had a related question, Steph. So I can see how when things are getting larger, or you're looking at how many of these kinds of things are there out there in the world, computer is probably the way to go. What other kinds of proof methods are you using, for instance, for those results where you had sort of bounds on the degree of a graph, for instance? How would you go about doing such proofs? Are they also computer aided? Are they hidden secrets of the trade? Can you share a little bit about your proof methods?
Yeah,
if you
absolutely.
can in this way.
Sure, yes. So this actually, I really wasn't kidding when I said the test of Wolfgang was so simple to state and yet so powerful, because all of those results, basically the bounds and things we got were like, okay, well, if you have this graph with a vertex of degree a certain size, then, you know, how can you chop up the graph into those partitions and which ones are missing? And so that was actually how we proved all of those results, is we just looked at the graph, and even Kai Zeng with his bound proof, that was how he did it, was looked at it and found out which of those connected partitions were missing. So super powerful and very unknown tool.
Steph, is there a reason to look at poset incomparability graphs and take them and color them? Like, is it just the combinatorial properties of the graphs, or was there a reason connected with posets?
Oh, that's a great question. Thank you. So actually, the original conjecture in 1993 was to do with immanence of matrices, and then that's how the posets came in. And then later on, Stanley realized when he introduced the chromatic symmetric function that that was how it was connected. So, so actually it goes back to immanence of matrices and then various reformulations as times come on. So yeah, back in the history, things were quite different. Great question, thank you.
There's a question on the chat.
Oh yes. Do existing sure positive results have representation interpretations? That is a really great question. So I believe that there is a graduate student, might be Anna Schillings, I'd have to check, who is working on the representation theoretic interpretations for chromatic symmetric functions if they're sure positive. So I'm not sure if anything has come of that yet, but that's a fantastic question. So right now, at the moment, it's not known, but it may be known soon.
Hi, Chef. So I have a question.
Oh, hi, Sheila.
Hi.
Wonderful to see you.
Yes, lovely talk. Do you have any explanation for why they're always rectangles, the ones that are negative?
That is that is I'd say it's $1 million question, but it's not a clay problem. So it's maybe the $5 question, maybe even just $5 Canadian. But yeah, doesn't that really jump out at you, as these negatives are all at rectangles and we have no idea why. We really have no idea why. And it's also pretty hard to prove, because the proofs we were using were basically using, for my paper with Angel and Samantha, transition matrices from the P's to the E's. And so as the number of parts go up, the proofs got way, way more difficult. So that's why the negativity results we proved, you know, they had 2 parts or 3 parts, and that was already hard enough. So rectangles, yeah, you got a lot of parts to deal with. But yeah, it really jumps out and we have no idea why that's true, but it always seems to be the case. No idea why. Thank you. Fantastic observation.
I had one last question on my end, but I think if there are other questions, they're probably more interesting.
All questions are interesting.
Well, thank you. So I'll just ask all the way at the very beginning, when you defined the chromatic polynomials and you were thinking about proper colorings and all of those, is there a way to develop sort of maybe a parallel theory about edge colorings, or is that at all interesting, not interesting? What would happen if you tried? Is it equivalent? No, nobody cares.
That's a very, very good question. So so I don't think anyone's looked at edge colorings. Possibly Kai Zeng has a little bit because he talked about line graphs. But yeah, that one hasn't been studied. I don't know if anything more has been done. Things to do with like kind of excluding certain subgraphs, which might be another natural thing to think about. That's been done by Angel. But yeah, edge colorings, I don't know. That would be interesting to see if you get anything new from that. That's a cool idea. Thank you.
Thank you for this
Excellent.
very, very interesting talk.
And thank you for all the questions. And again, thank you for the invitation. It's been a real honor to speak here today.
I guess we are going to stop the recording right now, but please stay long, and then if you